Is it okay if I use my program, graphing calculator program, instead of your graphing calculator, TI-84? So we have to assume that this thing is either going to intersect or is really going to be a circle within a circle. So it might be good to graph how this thing is going to look like. And with large numbers like 19 and 10 and stuff, so there might be some big shifting and things like that happening. So you should be prepared to adjust your window. So the nice thing about this particular graphing calculator program is that I can adjust the windows quite easily. So I can zoom in and out to get a better idea of how this thing's going to look like. Now I need to identify the different graphs, right? So the first graph is the blue graph. Second graph would be yellow. I can't see yellow. Red. If you're colorblind, can you distinguish between the two colors? It's the red-green look-alike. Is that what it is? Anybody know about? So there's no red-blue. So the red and green are distinguishable. Is that correct? The red and... Okay, well, in any case, let's read the directions again. The area of the region inside the first curve and outside of the second curve. So inside the first curve and outside of the second curve. All right, well, let's take a picture of this and then we can draw on it. So inside the first curve and outside of the second curve. So this is the second curve over here, inside of the first one, outside of the second curve. Would be this area. That's the area that we want. And what else we want, what else would be useful for us would be the angles that would make these areas, because we're going to need the starting and ending angles for the areas. So we're going to be interested in angles where these two graphs intersect. All right, usually to find an intersection we can just set things equal to each other, and that kind of would make sense here. Let's set them equal to each other. 19 sine theta equals 10 minus sine theta. Let's add sine to both sides. And then let's divide. So we got like pi over 3 or something like that. So this is where you would need some trig. And then if this is the pi over 3, and then you notice that the graph, is it pi over 3 or pi over 6? Pi over 6. And then you notice that on the other side of the graph, there's going to be your ending point over here. So we need to know what this is. Reference angle of pi over 6. So that's, I think, an angle of 5 pi over 6. And it'll intersect in infinitely many more angles, but these are the two specific ones that we're interested in. Now, the formula that we had just found an area within polar coordinates, but now we're talking about two different sections. And so if you imagine a sector, let's go back to the formula for the sector. If you have two radial distances, R1 and R2, so the area of just this shaded region should be 1/2 R squared theta R2 squared theta minus 1/2 R1 squared theta. And then if you simplify this out, we can use this to build our formula, or we can revise our formula a little bit. If we factor out a 1/2 and then we factor out a theta, which turns out to be our d theta later on, we can look at the two functions, f of theta, f1 of theta, f2 of theta, to be these two r functions. So the outer one is R1, the inner one is R2. So these are our two functions. And then that's it. Area is going to equal to the integral from pi over 6 to 5 pi over 6. And 1/2, we can squeeze the 1/2 outside. And then the two functions that we're dealing with, the R2 function is the 19 sine theta. We want to square that. Minus, and then we got 10 minus sine theta, square that. And I think that's all we need. We can punch this into the calculator or to Wolfram Alpha and see what kind of values this particular program is going to be expecting. It might be expecting exact values, or it might be able to handle an approximation. Let's see. I'm going to go ahead and use Wolfram Alpha for this. Am I connected? So there's a 1/2, and then there's an integral of 19 sine t squared minus parentheses 10 minus sine t close parentheses squared. And then our t value goes from pi over 6 to 5 pi over 6. $358? Okay. Did you multiply it by a half?
Oh, times by half. 179.038.
Perfect. All right, so let's see if that'll take that answer. 179.38-ish. Um, 179.04. what I got. Let's try 179.04.
Just wants like a simple pi. Like if you had to practice another, and like get a run with the answer.
So Wolfram says it's 1/2 times 110 square root of 3. Plus 160 pi over 3. There you go. All right, so.
But on a test, you would take 179.04, right?
Yes.
Okay.
Okay. So maybe it might be good practice to use Wolfram Alpha as a tool if you don't have a good integrating program, calculator program that would give you the symbolic result. I'm a little disappointed they didn't take this approximation.
Yeah, it's kind of weird.
Now, WebAssign's always super anal about how it takes the inputs.
Sometimes it might take it.
You don't get approximations when it says it.
Yeah, when it says
round
input a
up.
decimal.
We're making sure
Let me try more decimal places here. Did anybody figure it out? It's 179. 0.039. Yeah, so let's try this. So sometimes it does take those values. If you round off a little too much, then if you're not sure about the accuracy, usually 4 or 5 decimal places would take the place of it.
I've never seen it like that. All right, so 4 places.
At least 4 places, yeah. Yeah. So I had a feeling this would happen because there's a couple times where it didn't look like it cared what you got, but when you type in a number and you put in enough decimal places, it might be okay. So in this case, it worked out. So
for the next problem, I was confused by what it meant by it intersects at a pole. Is that just where like a horizontal vertical?
a pole usually means something is undefined there. All right, let's try. Let's give this one a try. So find all points of intersection of the curve. Again, I would want to draw it out to see where they intersect. So my two functions, 1 minus cosine theta, and then 1 plus you probably should go. You probably.
The graphs are not really weird if I change it to radians. That was like a solid.
It should be in radians.
Okay. Weird. Maybe I messed up.
So it looks like this thing intersects in three places. So there's a clear intersection here, and there's another one, looks like they intersect at 0, 0, and then there's another small one over here that they intersect in. If you zoom in, looks like they would intersect there too. So order your answers from smallest to largest theta. So let's try to do this analytically first, and then we'll take a look at the picture to confirm our work. Again, we're looking for intersections, so we're going to set them equal to each other. So it looks like the ones would disappear, and then this would be just sine is equal to negative cosine. And you're kind of just interested in, well, yeah, if you want to go tangent. Negative 1. So it looks like negative pi over 4, 3 pi over 4, those angles. Because, you know, root 2 over 2, the pi over 4 is root 2 over 2, except you want it when the angles are negative from each other. So all students take calculus kind of thing, whatever. So the tangent is negative in the first and fourth, in the second and fourth quadrants. So we got a bunch of angles like negative pi over 4, 4, 3 pi over 4. So it looks like it's pi over 4 plus pi and pi or something. Where n is positive or negative. No, negative pi over 4. Mm-hmm. So actually, we want the angles between 0 and 2 pi. So 0 and 2 pi. Right here. And then 7/4 is somewhere over here. Is that okay so far? So we want to put those values in to find our R value. So 3/4, 3 pi over 4 into either one of these should give us the same answer. So 1 minus the cosine of 3 pi over 4 should give you the same value if you put 1 plus sine 3 pi over 4. So this is root 2 over 2, I think, right? 3 pi over 4, cosine is negative, all students. So S, sine is positive. Cosine, this is in the second quadrant. And the cosine is negative in the second quadrant. So this is 1 minus negative root 2 over 2. So your R value is 1. Actually, I think, let me put it over here. 1 plus root 2 over 2, or simplify or combine, whatever. So this is your R value with a theta value of 3 pi over 4. And then the other one is 7 pi over 4. Sign? Oh, doesn't matter. And again, it's, I think, negative root 2 over 2. Positive root 2 over 2. Now, we only saw, based on our information, we only saw 2 intersections, right? Oh, based on our analysis here, we got 2 angles. And then if we look at the graph, we saw that there might be a third one, and that's at 0, 0. So I think that's what they mean by a pole when they intersect at 0, 0. So we should write a pole for the first one, probably. And then the first, the smaller angle is 3 pi over 4, and so this has a 1 plus root 2 over 2. And then the next one is 1 minus root 2 over 2 with an angle of 7 pi over 4. All right, let's check. Say capital, does it matter?
Yeah, I want to say capital.
So this is a 1 plus 2 over 2, comma 3 pi over 4. And then we got a 1 minus square root of 2 over 2, 7 pi over 4. Is it all right? First one, too? Yep. Yeah.
You got 7 pi over 4, then you just added pi to 3 pi over 4?
Yeah.
Because you weren't looking for that pi, right?
Yeah.
Okay.
Because it's all the values, all the angles between 0 and 2 pi.
Yes.
And there's many more, right? Negative pi over 4, which we didn't count, and then keep going around. But we're only going to go between 0 and 2 pi. All right. Any questions? Good. Yeah. Well, just because in our graph, well, first of all, the question is looking for 3 answers. And when we did our work, we only found 2 answers. And second of all, when we looked at the graph, it actually did intersect at 3 places. And the other place that we didn't find is at 0, when r is 0. And so that is what they would consider a pole, if it intersected there. Okay. Any other questions? All right. Yeah, so you guys will have a quiz tomorrow. The quiz will cover some stuff from parametric equations and probably some finding the areas in polar coordinates.
Would there be any sectors maybe? Or is this a sector?
Yeah, it was finding areas like a sector. So you should remember the formula for finding the slope or finding dy dx from parametric equations. And you should also remember the formula for the area in polar coordinates, finding the area in polar coordinates. Okay?
And if we need an arc length as well?
That's not going to be in the quiz,
Okay, cool.
but, you know, be good if you did know. The formula for arc length. What else was I going to say? Oh, I was going to say that if you hadn't noticed already, the homework assignments have due dates now, at least the first few. So January 29th, our first two homework assignments are due. The lab assignment is also due, the first lab assignment is also due on the 29th. And then I'm trying to make this so that the lab is due like a day or two before we're going to talk about that particular topic. And the lab assignments are meant to be like a reading assignment. You know how math teachers always tell you to read before coming to class? And this is a section that you would read, but then nobody ever does. I'm sorry for those people that actually do, but I never did. When I was a student, I never read. And so the idea behind doing these labs is to force you to look at some examples. And these are different from the homework assignments in the sense that they are just like the examples that they have in the book. If you were to read through the book, they'll give you concepts and ideas, and then they'll say this is an example. And so they walk through the example. Well, these assignments are like that. So they don't look like your typical homework assignment. And let's click on one of them to get started. Click here to begin. Now, their questions here are step-by-step questions. They don't look for the final answer. They look for all the intermediate steps. And so when you're doing this, you have to be careful and don't get frustrated because there's some things that you, as a student, probably will think, oh, if I was doing this problem, I would skip over this step. But this is going through step by step. And so there might be things that are obvious that you have to type in, but just type them in. Distance between a point and the xy plane is absolute value of x. So let's try that. So the other thing is that if you skip, you cannot go back. So if you can't figure out an answer, then you're not going to be able to go back. But that's okay. Just keep going with the work. Okay.
Are you allowed to completely restart the lab?
I don't know. I don't recall if there's a restart, but you could try and see what happens. So if you submit and you get it wrong, I think you have a chance to change your answer.
You have the same number of tries on the lab as you do with a regular assignment, just like 100.
Yeah. The difficult part is that if you really don't know the answer, then you're going to have to just skip it. And if you skip, one or two out of like 3 of these problems, that's not going to be that big of a deal. But if you end up skipping everything, then you should probably read the book. And if you read the book, like I said, these are exactly coming from the examples. And so if you look at the examples, they go through step by step, and then you'll see exactly what you need to do. Okay? Are they what? No, numbers change and stuff like that, so they'll be a little bit different. All right, so those are labs, and the idea behind the labs, again, is to get you to look ahead before you come to lecture so that when we come to lecture on Monday next week, you guys would have gone through this particular lab assignment, so when I talk about it, you'll have a good idea of what it is we're doing. Okay? All right, any questions about labs? Yeah? No, it'll just be all on the computer. And so I usually tally up the grades. I download the grades from WebAssign and I transfer it over to Canvas around test time. And I do allow makeups for homework assignments, but I don't allow makeups for labs. Yeah?
Do you have to give you written proof that we just actually did the homework? And
No. I thought about doing that. You know, some instructors do that, and I think that's a good idea. You guys are all adults now. You guys are mathematically mature students that I don't need to check your work. So, no. Yeah. So the thing is that, that doesn't mean you should slack off. I think it's still a good idea to have your work done on a nice notebook that you can refer back to. Because when you're studying, chances are you'll look over your homework and you see your homework and then you got an answer that you put there, but if you don't remember what you did, then that's no good. As shorthand as you need to be for you to learn from it to prepare for exams. All right. Let's get past the philosophical aspects of the course and just go back to our new section. So section 10.5 begins the study of conic sections. So conic sections are a way to describe a relationship between the x and y variables as a graph. And then the graphs that result in these types of equations result in what they call conic sections, which is a couple of cones and then pieces of a cone that intersected with some plane. And so I guess it might be a good idea to start thinking about that, since we are going to look at three-dimensional things in the future. So maybe before this, let me preclude. Yeah, so let me preclude this conic section discussion, or that first example that you saw, with a graph of a couple cones and the plane. Let me redraw that plane again. And depending on the tilt of the plane and how you cut it, you would get different shapes. So, for example, if you cut it like with the same angle or slant as the side of the cone, you would get the intersection to be some sort of parabolic shape. Like if you cut it with a plane that's absolutely perpendicular to the cone, you would get a circle. If it's a little bit slanted, a little slant there would give you no longer a circle, but more like an ellipse. And then if you cut it with a plane that's going vertical, going up and down. Oh, that's too small. Then you would have hyperbolas. So the idea is that these shapes come from a cone and a plane intersecting them. And then, so that's why they're called conic sections. All right. Now let's take a look at one conic section that we're kind of familiar with already. And we're going to take a look at this from a slightly different point of view. We're going to take a look at this from a point of view of what they call a focus and a directrix. So the definitions of these conic sections are based on basically focus points and directrix lines. And the definition of this first one is a graph that you would get that's equidistant from a point and a line and equidistant means any point floating around in this plane that has the same distance from this point to that, from the focus to that point and that point back to the line, perpendicular distance, would be part of your parabola. So the first point to look at would be the one that's right directly in between the focus and the directrix. If I randomly pick a point over here, the distance from that point to the focus is clearly larger than that point to the directrix, right? So that's not a point that's included in my parabola. Are you guys taking notes in pen? I just erased it. But there are thousands and millions and infinite number of other points that have the same distance between the focus and the point and the directrix. And when I say distance, I mean like the vertical perpendicular distance. So if we line up all these points, or if we plot every single one of those infinite number of points, what you will get eventually will be a shape that kind of looks like a parabola. So every single point on this graph has this property where you have the same distance from the focus as you do from the directrix. Okay? So that's our definition. Parabola with a vertex point at BC and a focus at B, comma, C plus 1 over 4a, and the directrix given by the line y is equal to C minus 4a is described by this equation. And the parabola opens upwards if a is positive, downwards if a is negative. So it turns out that these parabolas have this special property where we can identify the focus and the directrix. Let's take a look at probably the most popular parabola that we know of, as y is equal to x squared, right? We know that that's a parabola. We know that it has a vertex at 0, 0. It opens upward. So if this is your parabola, this parabola has those special, well, it has those special elements. It has the focus and it has a directrix. So we should be able to find out the focus and the directrix of this parabola. So if I rewrite this in terms of a parentheses x minus b quantity squared plus c, and figure out what a, b, and c are, then I should be able to find that information. So y is equal to, maybe a is equal to 1, and maybe b is equal to 0, and c is probably also equal to 0. So if we identify this parabola this way, then we can use these components to help us find the vertex, the focus, and the directrix. Yeah?
What if you can't always arrange the parabola into that form?
Into this form?
Yeah.
Yes, you can. You should always be able to arrange a parabola into this form. How? How?
1/4 x times x minus 4, so 1/4 x squared minus x.
Well, we'll need to talk about that a little later.
So what do you do next?
Well, let's finish this case first, and then we'll take a look at the homework that you're working on. So the vertex should be what? We knew that already, right? Now the focus, where's the focus? So the focus is B, comma, C plus 1 over 4A. Right? So it looks like we are looking at 0, comma 1/4 as our focus. And then our line, directrix, y is equal to C minus 1 over 4A. So y equals negative 1/4.
Oh, you don't put the square on the
Okay. And that's it. Any questions? Let's make up a problem. Should we go forward in looking for the focus and directrix, or should we go backwards and, if we have focus and directrix, to find the equation?
Let's find the focus and directrix.
Let's find the focus and directrix. So let's make up a problem. So give me an example of a parabola of any second order polynomial. Plus what? Wow. Made it really hard now. All right. Now we want it in the form of what's it called? Perfect square. You guys remember how to do that? All right. This is called completing the square. And this is important for this. So what I'm going to do is I'm going to take a 7 out of the first two values only. I'm going to leave the constant outside. So if I take a 7 out of this, that's clearly going to be x squared. Now this is going to have to be a 4 over 7, yeah? And if you're not sure, just FOIL it back and or distribute it back. Now I'm going to take this. This is that whole song and dance with the middle number, take half and square it. So this is your term, your B term, 4 over 7. What you're going to do is you take half of that, and then you're going to square it. So this is going to be the magic number that you're going to add to make it into a perfect square. All right, so we can call that 2/7 or 4 over 14. So 7x squared plus 4/7 x plus, what did I say? 4 over 49? 16?
Divided by 2
Square that is 14 over 14.
It is 4. It is 4.
It is 16. 16 over 1.
You divide by 2.
Oh, we forgot.
Sorry, 14 over 1.
Are we good?
14 squared is 196.
Are we good? All right, now this is not a true equation that follows from the previous one now because I just added something. So I need to divide or I need to subtract. This is not correct. Why?
7.
Because in here, 4 over 49 was being multiplied by 7. So you actually need to subtract this thing being multiplied by 7 as well.
And then negative 28 over 4. That's a negative 28 over 4.
So we got 7x squared. Well, let's write it as a perfect square now. This is supposed to be a perfect square, right? And provided that we did things correctly, that you did things correctly. And then we could deal with this. 4 over 7, I guess. 70 minus 4. The 66 over 7. All right. Now it's in that form, when we just easily pick out the vertex. So the vertex is going to be, now we have to be careful on how this things look like, all right? It says x minus, what does it say again? X minus b. So we have to acknowledge that the b is actually negative 2 over 7. So negative 2 over 7, comma, and 66 over 7. That's your vertex. Your focus is b comma c plus 1 over 4a. So the same b, and then c plus 1 over 4a, and a is equal to 7. Suppose you can simplify that if you want. The directrix is going to be y equals, and then it's c minus over 4a. So that would be your directrix after you simplify it and stuff. Any questions? Okay. We good with parabolas? You can also have a parabola going sideways, where x is equal to something with a y, and it'll follow the same rules. So in the book they call it a theorem. I don't think it's worth a theorem, but so if we look at the orientation, it's just the equation is x is equal to something with a y squared. And that's the big difference between parabola going up or down or parabola going left and right. Okay? All right, good. Any questions? Let's take a look at ellipsis. So ellipse is a little bit different in the sense that they have two focus points. They also do have a directrix, but with ellipsis we don't tend to look at directrix. And I don't know if you've seen the whole idea of an ellipse being drawn out. If you put two nails on a board and then you tie a string connecting those two, and then you take a pen and then you pull it tight, and then you move your pen around, you would end up drawing the ellipse. So the ellipse are all points equidistant to two focus points, or foci. So that equidistance is like the string. The string's length will never change. And wherever you are with your drawing utensil, you're always going to have the same distance, the same sum of the distance from that point to each of these focus points. All right, the equation of ellipse now has x squared and a y squared. Both the variables are being squared. So the big difference between this and a parabola is that with a parabola, only one of your variables is squared. Here, both of your variables are being squared. So if you can somehow rewrite your equation to look like this, then you should be able to find the focus points and the center point. Now there's this other value of c which isn't really part of this, but we can we use it to help us find A and B and help us find the focus points. Okay? All right, so let me see if I can grab an example for the last 2 minutes of class. So this thing that I'm calling class examples would be just, you can ignore that. That's just a way for me to get some examples from the book. If you want to do it and try it, you can go ahead and mess around with it, but it's not going to count towards your grade. No, somebody asked about the show your work boxes. So ideally, if I was collecting your work, then that would be the show your work business, but I'm not going to collect it, so you don't need to worry about that. Whoops. All right, here's a good one. I don't know if good one is the word for this. Looking for vertices and foci. Yeah, so I don't think we're going to finish this, but let me just start off by talking about completing the square, because it all really boils down to completing the square. So you want the x's together, and if you have the option to bring the constant to the other side, go ahead and do that. X's together, the y's together, and then constant on the other side, and then do that trick where you take half of the b term and then you square it. So this would be x squared plus 2x plus 1. So half of 2 is 1, square that is 1. And here you have to factor out the 3 first. And then, so half of 4 is 2, you square that, you get 4. And then now whatever you added on one side, you have to add on the other side. So you're not subtracting anymore because you're working with two sides here. You get that this is a minus 10, right? So minus 10, you added a 1 to the other side, and then you added a 4, but you actually added a 3 times 4. So then that's what you get on the other side. Yeah, it's a plus 1 plus 12. So 10 plus 1 plus 12 is 1 or 2? 3. 3? And then these are all perfect squares now. X plus 1 quantity squared, 3, y minus 4 quantity squared. And then to get it to look like an ellipse, you need this to be 1. So this would be x plus 1 squared divided by 3. And then the 3's cancel. Y minus 4 divided. Sometimes I want to look at it make it look just like the ellipse form. And so I might be interested in putting a 1. And then I might be interested in putting a square root of 3 squared here, just so I can identify these as A and B. Because that's what the formula is looking for the denominators to be squared. Okay, yeah? The plus 1 plus 4, this is actually not 4, it's 4 plus 12, right? So you added a 1 here, and then you added a 3 times 4 here. Minus 2? Yeah. Okay. All right. So the Learning Center and STEM Center is having some open house thing. If you go there and get some stuff signed off, and tell them that you're in the Math253 in my class, Professor Lapuz's class. I'm going to give you a little card. And if you give me that card tomorrow, I'll give you 1 extra credit point for the exam. Learning Center, STEM Center. Right now. I think you need to get some stuff signed, so you might need to go around and get people's signatures.